Hello there, welcome to the wonderful world of radio frequency and electronics engineering. Hope you're doing well. Well, on the bench for repair today is a power supply linear one, which has got a fixed output voltage of 13.8 volts with a maximum current of 27 amps, manufactured by a company called SkyTronic. Now the part number for this is, I think it's 650667. So that's 650667, and I think there were multiple models of these with different current ratings on them, and I think they also had some that had variable output on them as well. So there's a whole range of these power supplies available. So we'll have a look at this power supply, see what's wrong with it, but straight away there's a couple of warning signs that I can see immediately, and this is what prevents me from plugging things in just straight away to see if they work. The fact that we've got some screws missing on the power supply. If we look round it, there should be some screws here. This is sort of loose in the back. The screws missing here and here. We've got a couple of screws in there, nothing in the top. These two are empty, and these two screw holes are empty as well. So that's a warning sign, obviously, that somebody's been in it before. Likewise, screws missing there, but we've got two screws in there. So that tells me, alarm bells start ringing straight away. That tells me that somebody's been in this. So I wouldn't go then plugging that into, you know, mains 240 volts at this stage, because you never know what's inside. So first thing we'll do, I think, is we will just verify that there's no other physical damage or anything like that on the unit. I can see here that there's the series pass voltage regulators on the back. It's nice that they've got covers on them, because the cans are collectors and they're live in essence, even though it being probably sub 50 volts, but still there's a potential for negative connection from the front or from a chassis part of a radio that this may be powering, for example, that would touch these collectors and then cause a short circuit on the high current side. So they've taken some care to protect those. We've got a fuse on the back as well. It's not a fan cooled one with the look of it, because obviously the heat sink's on the outside and there's no fan assembly. So there's no other damage from what I can see, other than just screws missing. Everything looks okay. So we'll just whip the lid off and have a look inside then and see what surprise. It's always advisable to do this when you've got a power supply in this kind of condition, because I've had them before on this channel where, you know, somebody's had a look inside. The power supply's been around the houses. Numerous people have had a look and a go at it. Maybe some inexperienced people as well, and they've disconnected things, left wires hanging off. And I've had them where the mains cable, live and neutral's been touching the case inside, and, you know, things not terminated properly, components put in the wrong way around, all sorts of things like wires off and you name it. So, you know, expect the unexpected, I think, with this. That's the way to go with it. And just whip the lid off and have a look inside first before we plug it in, because you never know. I've seen Kit Kat foil covering fuses, things soldered across fuse holders, so we'll have a look. There's no, sometimes I put a little circuit diagram, you know, just here on the inside, but there's no diagram, unfortunately. Anyway, let's have a look inside, see what we've got. Well, straight away, that doesn't look too good, does it? There's a component there, look, taped down, a resistor with the look of it, taped down to the top of that transformer. So there's something there. So somebody's definitely had a go. But yeah, just looking at the architecture. So just whiz it round this way a bit, have a look. So it looks to me like, obviously, we've got the mains in coming in there, the live side going to a fuse on the back, which is this part here. Then we've got the cables coming down to what is this rocker switch on the front, which has also got an internal illumination, neon illumination. So both live and neutral paths are switched, and then the output then is fed straight into the bottom coil on the transformer winding there, which is a primary side of a transformer. We've got the mains earth as well, the safety earth connected to the transformer, as well as down to the chassis down here. So that's quite good for earth protection. Sometimes you've always to watch where these screws are, that particularly if you're using like self-tapping screws and things like that, it doesn't gnaw into the cable, and normally that will be protected with some kind of heat shrink protective sleeving, because the threads of the screw would potentially bite into the cable. But yeah, other than that, it's a fairly basic common power supply architecture with the look of it. So it looks like here we've got a full wave rectifier, which I've seen quite a lot before on these kind of power supplies. Rather than use a bridge rectifier, which bolts down to the chassis, one of these square type devices that you can get for a lot of power supplies, what they do to get the higher current for longer duty cycle is they actually use individual diodes and they parallel them up. This is a centre tap transformer, so we've got the secondary windings here. These are the high current outputs, which are delivered by these thick copper cables. They go to these diodes, and with the look of it, because there's only one, there's a cluster of red wires there that go off to the same point. So basically it's using the centre tap of a transformer's output goes straight to this PCB down there, which comes in and solders with the look of it here, and that goes to the negative side with this copper clad, obviously negative side to both these electrolytic capacitors, which are the smoothing capacitors. We've also got 4 down there, so all the negative sides of these capacitors connect to what is the centre tap of a transformer. And basically top and bottom of it is that the negative connection there, or 0 volt connection as it's termed as, that would then go out then to the negative terminal on the front, or the 0 volt connection there for the binding post on the front, the negative one, the black post. So that's basically a common ground path, is that. The positives then are derived through this board, which is the full wave rectifier board with the look of it, because we've got 2 clusters of diodes on each side of the board, and they then form a full wave rectifier. And then with the outputs of both those diodes then are essentially joined together, which is this red cable that's going down there, which solders to that point just there. You might be able to see it just there, look. So it's a common area. Now the output of that goes straight off then to what is this reservoir board here, but as well the other 2 go off to what is the transistors, this transistor being the driver transistor for all the ones on the back. And ultimately then the other red wire connects to all the collectors, or the cans of all these TO3 transistors, series pass transistors on the back. Now it looks like here we've got a regulator board, so this looks like that's a rectifier board, that's a filter cap smoothing capacitor board, and already I've seen something that's a little bit dodgy there. Look, the clip that holds it down to the casing's broken, so we're going to have to fix that. We've got this regulator board here, which I suspect is where that resistor's probably come from, and I reckon it's probably on that board somewhere, so we'll have a look at that. This looks like it's got its own power supply derived from the transformer, so the regulator board is working from an independent power supply with the look of it. Now it looks like as if there's a lower current winding due to the thinness of these wires from the secondary here, that is again derived through these 2 diodes. Now they could have just used one side of this effectively to the negative line on this this part of the board, and then obviously the positive side to one of the diodes, and then ultimately smooth that with that cap down there, and then generate the voltage that way with the isolated effect of that secondary winding, that separate secondary winding, the ground path from that capacitor down there connected to this board, and then ultimately out that way. But I think what they've chosen to do is they've got a centre tap on this winding too, because both of these diodes are in the same orientation. So you've got both wires, if you like, from the transformer. They essentially solder onto these diodes, and the diodes, which are these 2 here, the 2 wires from the transformer, in the same orientation, and they go to this track here, which is then where the reservoir cap, just those 2 terminals, are soldered. So there's no actual ground provided by that circuit, if you like. So it must get it from what will be this board. So it must be that the centre tap of this winding is connected to the centre tap of this. So it may be there are 2 wires, a 3rd wire that comes out of there. There could be two little wires in there. I'd have to unwrap that to verify it, but I suspect that's what there is. There's effectively 2 secondary coils, both with centre taps on them. So we've got what will be 1 secondary coil, which is a low current supply there, with its centre tap coming up this sleeve here down to the common earth connection, if you like, or the 0 volt line. And then the other 2 then windings, the outer windings, if you like, of a transformer, then go off to this part. So we've got a effectively with this blue wire, probably, oh no, there's another wire down there somewhere, that's it, the other wire's down here, would connect then the board that way. So in other words, it's getting its ground for this board from here. So that's how they've chosen to deliver it with the look of it, because otherwise the circuit wouldn't work, because obviously we're just getting positive here, and then that would technically would be isolated then from the secondary winding, the high current side. So I think there's definitely going to be down there probably 2 wires, and I can verify that by having a look down there, and there is, yeah, there's 2 copper cables. If you look down there, you'll be able to see, and just bend that out of the way, maybe zoom in a little bit, so you can see it there, look. So I think that's the one of them's a centre tap from one of the secondary windings, the other's a centre tap from the other secondary winding. So that's how that works. So this gets its own independent power supply from what is this this transformer. So again, another full wave rectifier. Then obviously we're getting the supply to this board smooth by that capacitor. We've ultimately got a voltage reference circuit that comprises of a Zenner diode. I can see a missing component here, which presumably is going to be this, in series with the Zenner diode. It looks like the voltage reference Zenner diode circuit. Let's have a look. Yeah, looks like that resistor. If I can get my little pointer stick and point it out, but basically there's a little resistor. I'm just going to see if I can point it there. There's a Zenner diode there, and then the resistor that will be in series with it to set up the Zenner diode potential divider is just there, that resistor there. So that, I'm afraid, is I think it's R2 it's called, yeah, R2's in line with D3. So you've got D3, which is a Zenner diode that sets the voltage reference there, look. And then you've got R2, which is down there. And I think that is the series resistor, is this. Looks like it's baked a bit. But they do bake these resistors, so that might not be the fault. It could be the fault's being misdiagnosed. We can always check that though. But there is a bit of discoloration, and you do find that around this area. It looks like somebody's been hard at it, chiseling away at this board with the look of it. And we've got a bit of print there, look, and that one needs repair. I don't know what the heck's got on there. That looks a bit, how are you doing? So we'll have to have a look at that. But generally the architecture is quite common. We've obviously 4-wave rectifier, reservoir smoothing board, voltage regulator PCB. This looks like it's got an output transistor on it that is effectively the current amplifier for this voltage regulator circuit. This then drives this transistor on the back. Obviously this then gives a higher output current to drive then what is the 4 big series pass transistors on the back. So in essence it's like a Darlington arrangement where we start with a smaller current gain, lead to a bigger current gain, then followed by ultimately what is the output series pass regulators on the back. So that's that. So yeah, in previous videos obviously we've had issues where the 2N3771s, 2N3055 power transistors on the back go collector emitter short. So ultimately then that can give the impression that the voltage regulator PCB is at fault when it isn't. It's the transistors at the back. It could also be the Zenner diode's gone completely short. I mean, if it's like 35 volts DC across that Zenner diode, and potentially in the middle there you've got that potential divider architecture where you've got the resistor in the ground path, and then basically what happens is then the centre tap between them is a voltage reference source. So basically it could be that the Zenner diode's gone dead short and it started to cook the resistor, but often these resistors are chosen to have a lower ohmage anyway to develop the required current in the circuit that's required then to output and drive. Looks like we've got a potential divider, a potentiometer rather, just down here for setting the voltage. So looks like we've obviously got this transistor ultimately would amplify the current from the Zenner diode, and obviously produce then the right current drive for this transistor that's mounted on here presumably. This potentiometer sets the reference voltage, so ultimately then for regulation we can control the power supply's regulated output using this potentiometer. Set the fine adjustment of the voltage. So we'll have a look at this resistor now that appears to be burned or whatever, and we'll just get that on the bench and have a look and see what's wrong with that. Okay, so let's have a look at this little resistor that I've saved from the transformer. So here we go. Right, let's have a look at it and see what condition it's in. So we'll just use our little magnifier, and as we can see there, oh, that's good, it's showing good signs. It's not burned. I certainly didn't notice it had a black charred smell like they normally have, where they like a barbecue smelling. You know, you really know it. Anybody who's burned a resistor out knows that the stink that they give off. Well, this isn't showing that sign, and certainly no smells like that. Now the spiral swirl on the outside I believe is a resistance material, and the inner part is like a ceramic insulator, and the resistance material is in good nick. Now if that was burned up it would be all black charred like coal in the middle, and it isn't. It's okay. So I'm just gonna try and flip it over on the other side and have a look. Again, reasonable condition. Can't see there being a problem with that resistor, to be honest with you. We'll know in a moment because I'm going to measure it now. But what I'm expecting is, obviously in this circuit, there tend to be all preferred values of resistors, and as we know, resistors go in stepped value ranges of preferred values, and then you get the non-preferred values as well, which you tend to order separately, and they've got much higher tolerances for the middle ranges in between the preferred values. So I've got my meter here. I'm looking to see whether this resistor's gone high resistance, gone open circuit, burned out, whatever. So this is what we need to ascertain. But it looks good, to be honest with you. It's just the ceramic sort of paint on the outside where the resistor colour code's normally printed is missing. So it's crumbled off, which is to be expected with long usage and high heat over a long period of time. So it's just, I've got to be careful don't flick off onto a carpet because I'll never find it again. So, oh, that's good, 220 ohms, so that's spot on. That's what I'd expect to see. Now if there was something wrong with it, i.e. that the burning of the component had burned away some of the conductive material in the resistor, then that value wouldn't be reading a preferred value resistance of 220 ohms, because that is actually a correct preferred value. If it was reading a weird range in between the preferred values, then I would be looking at that further as that component being failed. But that's a good sign. 220 ohms, you know, as a preferred value, it's spot on. It's not high, it's not gone low, it's not got in between values, it's not reading weird. Obviously we don't know its actual value, what it was originally intended to be, which I'm assuming is going to be 220 ohms, because otherwise it would be reading off, and it isn't. But if we could only tell what original resistance colour code that had to start with. Okay, so another thing to consider is that that resistor isn't the fault. Although it looks as if it could be the fault because of its condition, it may not actually be the fault. It could be that the Zenner diode's gone short, or there's a transistor blown, like we've had with the other repair videos we've done. So I'll save that resistor in a nice safe place. Okay, so what I can do now when I get my pen is we can just demonstrate the sort of what happens to these resistors in essence and do some mathematics. So if we've got like a 30 volt rail, okay, which is essentially coming from our bridge rectifier, so 30 volts DC, we've got our 220 ohm resistor, okay, and that's the one that's been sweating and all we've just been looking at. And then ultimately then we've got our Zenner diode, which is what we're looking at on that board. And then we've got a 0 volt line there, okay, which is obviously our ground reference, if you like, coming from the rectifier circuit. And then off the centre tap here, between the Zenner diode and the resistor, is where we take our potential from. Now, that could go to either a transistor circuitry, ultimately, and then ultimately that then could go out into what would be a potential divider, because you saw one of those on the board, pardon me. And then ultimately that could drive another transistor, and that would then effectively be the output regulator to what is the big transistors on the back. And then ultimately we've got a collector supply there, and these could be NPNs, it could be PNPs even. But just hypothetically, this is an hypothetical circuit. And we've obviously got that kind of a sort of Darlington arrangement, current amplifier. And therefore we can set the voltage with VR1, which is the potential divider, potentiometer rather, that we saw on the board. And that would set then the output voltage here. So let's say, for example, this is a 15 volt Zenner diode, okay? It may not be, it could be any voltage, but in our hypothetical situation, it's 15 volts with a 30 volt supply. Now, if this Zenner diode goes short circuit, so in other words, all 30 volts is derived across that resistor, we need to know what power rating that resistor would need to be in order to take that kind of current and voltage across it, which will obviously get it to heat up, depending on what value it is. And so, as we know, resistors are manufactured in different wattages, so you got just, you know, quarter watt, half a watt, 1 watt, 1.5 watt, 2 watts, so on and so forth, right up to big massive resistors. So in our case, this little tiny one that we had in here is a quarter watt with the look of it. That barely stand quarter watt before it had just burst into flames, I think that. So that's a rough idea of what wattage that would be. So we can do some mathematics. So as we know, if we use the VIR principle, okay, the V, I and R, essence, we've got multiplication between current and resistance, and division between voltage and current and voltage and resistance, etc. So this is the sort of principle we're going to be using here. So we've got 30 volts. So basically what we're going to do now, we're going to calculate what the current of the circuit would be, assuming this Zenner diode is short circuit. So 30 volts is across that resistor. So volts multiplied by, divided by resistance gives you current. So if we divide that by 220 ohms, that will give us a current of 136 milliamps. So it's drawn in this case in amps, 0.136 amps, which is 136 milliamps. Okay then, so now we know the current that is taken by that resistor when it's got 30 volts at 220 ohms. We now need to calculate the wattage consumed by that current, basically, well, that current would generate in wattage. So again, we're going to do again the calculation again. So 30 multiplied by 0.136 amperes, which will give us wattage, and in our case that works out to be 4 watts. And that's a big wattage in comparison to what we've already got in that circuit. So that resistor is going to get very, very hot indeed, without a doubt. Probably burn up eventually, or may not do, depending on how good it's manufactured. But it'll certainly get very hot. Okay, so if we assume then that the Zenner diode is working 100%, okay, and that there is 15 volts across that Zenner, obviously half a supply is essentially being quashed by this resistor. So we know we're going to get 15 volts between that point and that point there, if we were to put our multimeter there. So we can do the same equation now, but in relation to 15 volts. So 15 divided by 220 ohms equals a current of 0. And this is where you've got to be careful, because a few of my apprentices in the past have messed up here. Amps. That is 68 milliamps. Now, a lot of apprentices that I've had over the years would just think it was 6 milliamps, and it isn't. It's 68 milliamps. Okay, then. So it's how you read it, obviously, because 1000 milliamps is 1 amp. Okay, so 0.136 is 136 milliamps. Again, 0.06 is 60 milliamps. So, you know, it's how it comes out sometimes when people do calculations. I think it's, you know, 6 milliamps. It isn't. It would be 0.006 if it was 6 milliamps, and a lot of people fall into that trap. So, of course, now we've worked out the current, we need now to work out the wattage. So 15, again, multiplied by 0.068 amperes equals a wattage of, and if you shout it out at the camera, it's 0.9 watts. So that would be less than a 1 watt resistor in that particular case, in this example. So as long as we select a higher wattage of more than 0.9 watts, we're good to go. That component will survive. Now, of course, if you're unsure when you're doing these mathematics how to work it back, you can use this principle quite easily. So you think, hang on a minute, have I worked the voltage out? Have I got the current and the resistance right? Well, how do I work that out then? Well, that's quite easy. You can back work it. So if you want to work out the voltage that should be in the circuit, now that you know the current and you've obviously got the resistance, if you're unsure whether you've measured the current correctly, i.e. 6 milliamps versus 68 milliamps, you can do this calculation. So basically, you can take the current, the I, if you like, okay, you can multiply that by the resistance, and that will give you the voltage of the circuit. So if any of these values are incorrect, i.e. you've read them wrong, or that you've misunderstood, then the voltage will be totally wrong. We know the voltage needs to be 15 volts, so therefore we need to backwork this wattage measurement in order to get 15 volts again. So how do we do that? So we take the current be 0.068 amperes, which is in this case 68 milliamps. Okay, we multiply that by the resistance of 220 ohms, and that gives us 14.96 volts. So we're nearly at 15 volts, so we're bang on there really. Obviously the real calculation for this, if you were to go further down the decimal point range, is sort of like 0.68181818, etc., so on and so on. So if you include all these to the power decimal point this way, then you would essentially get to 15 volts, but we're only working to a certain tolerance, so 14.96 near enough is good enough. Had that been 6 milliamps, then that will come out at a totally different figure, and that's how you can back work it to check that your voltage measurements are proved correct by working the mathematical formula one way and then reversing it back the other, so that you can then calculate the voltage from resistance and current, just like you can calculate the current from the resistance and the voltage. So that's that. So it could be, for example, that this particular Zenner diode is maybe a 9 volt Zenner or something like that, and it uses a totally different type of regulator. It could be using PNP transistors, for example, so it's using a lesser voltage, which means this has to then drop a higher current across it, obviously, because whenever the voltage decreases here, the voltage increases here. So likewise, if the voltage is higher here, say this is a 20 volt Zenner, this resistor's only got to drop 10 volts. Or if it's a 25 volt Zenner, it's only got to drop 5 volts. You know, if it's a 10 volt Zenner, this has got to drop 20 volts, so on and so forth. So the higher the voltage across this resistor, the greater the current there's going to need to be, and the higher the wattage. Well, the current's regulated by the resistor, obviously, as we've worked out here with the mathematical formula. But what is the variable constant is a wattage. So that will change immeasurably as you're going up and down with the voltages. So any fault condition that occurs in this sort of area of a circuit there has a marked effect on what happens with this resistor. So what we'll do now, I think we'll take this Zenner diode out of circuit. We'll have a look to see what kind of Zenner it is, what voltage, and we'll do some measurements using a 220 ohm resistor in series with it to see whether the resistor, the Zenner diode rather, is short circuit or not regulating properly, and then we'll take it from there. Right, so I just got this little PCB out there, and it looks like as if, here we go, look, so that resistor goes here in that part, which you can see all the discoloration around the board. I thought this could have been the Zenner, but I don't think it is, because when I read the part number on the side, it looks like a 1N414, just ordinary diode. So I think D6 is the actual Zenner. But if I just look at that under the magnifier, I think you'll see it's a 1N4 something or other, and I think that's the Zenner, that's the baby. So that's like in series with the supply coming in. I think that's feeding the supply there maybe, and then you've got the Zenner after the resistor. So you've got some weird things going on there. So we'll just have a look on the other side of the board as well. Let's have a butcher's, see what we can see. And that don't look too good. It looks like somebody's been at it with a knife. So again, just try and get to that more focused. So let's have a look, see what we've got. So it looks like as if we've got a track that's broken there, and that looks like Crater of the Moon. That on the top there, that thing there looks awful, that. But this looks like it continues through and goes this way. So it looks to me like as if, yeah, this track thing here, we're going to have to spread back and link back to this. That looks a bodge job. I've no idea what's gone on there. There's all sorts of little bits here. We'll have to straighten that up. But with the looks of it, looks to me like as if, yeah, we've got a Zenner there, look, coming from here. So we've got again some weird sort of thing going on around here. Got a few components there. So that's the diode, the 1N whatever diode going from there to there, those 2 points there. What's this component there then? Is that a capacitor? Oh, that's a resistor, which is going down to here, and all this clad, which is ultimately, with the look of it, potentially, where's all that clad go to then? Positive. So that's like the positive supply then, going up to there, that resistor. So you get a positive supply from that resistor, then jumping across then to that top bit, goes to there. There's a capacitor as well, and then it jumps down through that diode then essentially there to this point, obviously to this what appears to look like this transistor. So it like supplies a voltage to that transistor, so that's independent. We have then, what is this, connected up to there as well via the other side of that capacitor for decoupling. With the look of it, we've got what appears to be one side of that. I don't think that, no, that transistor's got nothing to do with it, it's this bit here. So what's that then? That looks potentially like it's going to be another because the Zenner diode is there. That's the Zenner diode. It's across from there where my fingernail is to there, and then to the right of it is that resistor. So the resistor goes from there then to there, and then there's a bigger diode then, which ultimately then goes down to here, and that then goes up to this rail here then. Interesting. Right, okay. So I think what we're going to do, we're going to link this track back over, try and repair that, and we're also going to remove that Zenner diode and test that now, and try and smarten all these connections up, because that's a terrible job, is that. Somebody's had a right go at it, but you can see the discoloration on the board there, what the Zenner's left behind, and yeah, it's definitely been running. This discolorations from the resistor rather. It's definitely started cooking it a bit, but we'll measure some of these diodes anyway, lift them up and let's see what we get. Okay, so we've got it out the circuit, but it's a BZX55C, I think it is. Yeah, and it's a 3.6 volt Zenner, I think, according to this. So let's just put that on and let's have a look here. Just have a look, see if I can get it to come that way around. 3V6 it says there, look. I can hold it still, 3V6. So it's a BZX 55C 3V6. Always difficult to see when you're trying to handle them, impossible. No, BZX 55C. So these are, according to the information I've got on the internet, these are 0.5 watts. So the half a watt with the look of it, but let's just have a look here. Because the BZX55C is actually a family of Zenner diodes, and as such they are what would be rated, if you like, the same wattage throughout the entire range, I believe. So 5V1, so look at that one, see what this data sheet comes up with after I've got through all these cookie things here. So yeah, I'll see if I've got one of these, or at least a 3.6 volt Zenner. So it does look to me like as if yeah, but we'll measure it though, we'll measure it. Yeah, 0.5 watts, so you know they're not very high wattage at all. Silicone planar Zenner diodes, BZX55C. So they do the range from 2.4 volts to 120 volts, and you can order them in different ranges. But I'm just looking up the spec sheet here, so if we just have a look at the computer a second, we've obviously got the that one there, that's ours, this one that we're looking at, 3.6 volts. So again, yeah, when we're looking at that, I'm just looking at the rating, power rating. They're not very big power rating, only 500 milliwatts anyway. You know, as we can see up here in the top right hand corner, just up here. So they're only 500 milliwatts. So yeah, if we have to replace it, I'm sure I've got one in my parts bin somewhere, but I'll just set up a test now using a 220 ohm resistor and the Zenner diode just to check it, and then we'll test it and see what voltages we get. Back soon. Okay, so we built a test circuit. Now we remove a Zenner diode. We've got a nice new 220 ohm resistor there. We've got a power supply that's currently in our test circuit delivering 12 volts. And so we're just now going to go on to using our probes, our voltmeter. We'll just do some absolute voltage checks on the supply just to make sure we're getting the correct thing. So we're getting there like 11.98 volts, which is across these two terminals, if you like. That's where we're going now. And then ultimately across the Zenner diode, the ground and the middle tap there. And we're getting, obviously, you know, the same supply, basically 11.98 volts. So across there and there. So what that proves is this is open circuit. So yeah, this has got a problem. This diode, it's going to open circuit, and obviously this is then allowing the full potential. Instead of 3.6 volts clamping it, we're getting 11.98. So as you can see there, it's, you know, it's obviously an issue with that in our circuit. So what we'll have to do is replace this diode with a 3.6 volt Zenner. So we'll have a look in our parts bin and see what we've got. Right, so we've got the components in now, and we've done our best to repair this board from what it was like earlier. It was horrendous. So we've done some more resoldering, and we've bridged this track there, which was broken just there where my fingernail is. There was a breakage there. We've relayed that track that was coiled bent back, so we've done that. We've got that connected back. Everything's all nicely back as it should be, and cleaned up the board. And then on the other side we've got a BZY88 Zenner diode, which is that black beaded device down there. That is the same specification as the original diode that was in it. And then we've got another 220 ohm resistor. Now I was careful to read these are 1N4101s, I think they are, and that's a 4001, because sometimes the 1N series are Zenner diodes as well. So there are some in the 1N part range which are just not standard diodes, they are Zenners. So I just wanted to make sure there weren't two Zenners in there. So I've read the part numbers of these devices, these two diodes there, before I put the Zenner in, just to make sure they weren't going to get caught out with another Zenner problem. So all looks good. Can't see any bulging of the capacitors or anything. There's no obvious sign of any severe damage anywhere else. Obviously when we put the board back in and we sort out the other issue with that regulator board being loose, when we power it up, we're going to have to probably adjust this adjuster, which has got a hole through the back of the PCB anyway, so when it's in we can stick a screwdriver in and tune it and get it to the right voltage output. Now if you remember right earlier on, we were looking or discussing about the way this gets its negative rail or its 0 volt rail, and it comes from what is the terminals at the front. If you look here, we've got black and red wires. Now they actually connect to what is the post at the front. So in order to get its sensed output back so that it can regulate as the voltage drops, it relies on these black and red wires. But in addition to that, the black wire is the 0 volt return path line, if you like, for this PCB's power supply, which is these two diodes here. Because the centre tap of the transformer for the secondary winding for these two goes to this board first, and then effectively the ground wire, which connects, or the 0 volt line, to the black post on the front, also doubles back and comes up here and connects here. So that is where this board picks up its ground reference from, if you like, its 0 volt line, and then ultimately these two diodes are the supply, which is through this capacitor here. And you can see that when you look a bit closer on the PCB, because you can see just on the end here where the black wire solders, which is here where my finger is, we can see it solders just there, and it goes straight to the negative side of the electrolytic capacitor, which is just on there. So the red wire that's coming off the front there, this supply rail, solders here, and that's got basically a copper clad that basically goes round. There's a component there at the bottom, which is this capacitor. That's there, across there, and then it goes up here and round to there, and that's ultimately there where it makes its way in. It goes to this resistor, and then that's when it makes its way into the circuit then, in order to sense the output of the power supply when it obviously reduces. Because once we load the power supply, the voltages will start to reduce, especially when you get to 20 something amps. So to combat that, it sniffs the output of the power supply and keeps the regulation in abeyance. So that's how it does that, but it's doing it through transistors instead of integrated circuits and op amps like you get on most decent power supplies. This uses an old conventional method of doing it. This transistor here is a final output drive transistor, which then drives the rest of the regulation after this, which is ultimately these wires here, which then go off then to the rearmost regulator. Now the rearmost regulator actually has two series pass transistors on it, with a look of it. It's got one at the top and one at the bottom, and both those then, one presumably drives a pair on the back and the other one at the bottom drives the other pair on the back. So that's how that works. So yeah, interesting. So I think we just need to glue this PCB down, this regulator PCB there that just seems to be flopping around in the breeze. Just epoxy resin that in, I think, and tie it down somehow so it's not going to be a danger, and then put that back in and tidy the wires up, keep them all cable tied and neat and tidy, and then let's turn it on and see what happens. Now there still could be issues after this. We could have a blown transistor series pass regulator on the back. There could be other problems as well after this, so we'll just have to see. But we did find obviously a defective Zenner diode, which was open circuit, so naturally that's going to play havoc with the voltage regulation. Had we had turned the power supply on earlier, before we even found this fault, then the output would have probably just been full on, you know, full on regulation of the, you know, unregulated rather, coming off the collectors, emitters of these transistors would have almost, you know, just been connected together in theory. So the 30 odd volts DC that's present on these capacitors would have gone straight out to the terminals on the front and probably caused damage. Now we do have a capacitor which is across the red and black wires, which goes to the front terminal, and that's not blown yet, obviously, this capacitor here, and depending on what voltage it is will depend on, you know, whether it would have popped. But if it's about a 35 volt capacitor, then yeah, it would ultimately survive. But you can never see anything, can you, when you want to? Have you noticed that? What's this here? I always put a, I can't see it on camera because it's too so what is that? What voltage is it? 50 volts. So we're quite lucky there, because had that capacitor been rated at 25 volts, which would be more than sufficient for the output terminal supply being at 13.8, if the output of the voltage regulator on the power supply goes to maximum voltage output because of a fault condition, that electrolytic would have blown up. So it hasn't done, which is quite good, so that's good. Yeah, so interesting. We'll bob it back together and let's, fingers crossed, let's see whether it works. Okay then, so let's just have a look at the circuit diagram now on this particular thing, what we've managed to work out so far. So we know that we have the live coming in from the mains, we have a fuse, then we have what is a switch, and then likewise the neutral path from the mains is coming in, and ultimately that's going straight to the switch as well. And then we've got what would be the primary of the transformer. I've got the laminate core transformer, and then essentially what we've got two windings on the secondary side, and we've got secondary coil 1 and secondary coil 2. both of which have got centre taps coming off. So if we just take the high current, basically we'll call that H and that L for low current. The high current side has got two ends of the transformer going to what is a diode pack. So if I just draw that in there like that, and we've got more than obviously, you know, one diode, but I'm just going to, a couple of diodes, so I'm just going to basically illustrate that by just drawing two in. But as you've seen earlier, there's lots and lots of diodes making up that pack. Now the output of those two is joined together, and that is the positive line there. And what we have then, the centre tap of the transformer comes this way. It's going to leap over, and then we're going out here. So the secondary winding, the low current secondary wind centre tap, joins the centre tap from the high current side. This ultimately goes out to what is the binding post on the front, which is our negative or 0 volt output. Here we have the usual thing where it goes off to what is a series pass regulator, which is on the rear of the unit. We've got a number of transistors. Again, I'll just draw two because it'll just get a bit wild. And those are essentially the output transistors on the back. We've then got this heatsink here, which is essentially the driver for these as well. So we've got what would be the drivers. Now each pack, if you like, because this is like just showing you one grouping of those series pass transistors, has its own driver transistor. So there's another one of these again underneath. So basically you've got 4 lots of transistors driven by 2 drivers independently, and ultimately that then goes off what would be to the regulator PCB, which we've just done that diode repair of. And again, this transistor here is on the reg board, and this ultimately is where we get the VREF, the drive if you like, coming in to regulate the supply. The output is going again to a binding post on the front. I cannot see any emitter follow resistors, but there probably is on the heatsink buried down there. There's probably some emitter resistors there just to balance out what would be on the emitters of the transistors, to balance them all out. Now we do have a supply coming off the positive binding post, and obviously the negative as well coming this way. We've got a sense line coming down here. So if we look at the VREF PCB here, that's coming in, that's an input. This is the 0 volt, so that's the sense line. And then if you remember rightly, we had the 2 windings from this transformer coming in ultimately, and that leaps over and comes down here, and then that's coming in, and we've then got, if you like, the diodes then on here which come off, joined together. We've obviously got the capacitor as well, which ultimately connects to this ground line here. So that's where it's getting then. Obviously we've got the resistor, and then that naughty Zenner diode that packed in, and then we've obviously got the transistor circuits and everything else coming off of that. Now we also, before I forget, just need to draw the capacitance in here. So again, we've got a bank of electrolytic capacitors, which are the main reservoir smoothing capacitors, which are just across the full wave rectifier. So that's a little rundown really of what we've been dealing with today. It's a basic rundown. It's not an exact circuit diagram of everything that's on the unit, but this is the gist of it, what we're getting. So yeah, another interesting thing. Obviously we'll put it back together, see if it works, but this voltage reference circuit here if that Zenner diode was to go, say, high, and all the voltage passes through, it'll force this into some kind of unlocked condition, because obviously as we draw a load across these two, what is the output, which we call RL, when we reduce the resistance here and we start pulling current off this, the voltage at this point starts to come down. So ultimately it starts to drift down, especially when we get to 20 amps. And the voltage here as well, likewise, at this point, that also, when we look at the voltage, that starts to drastically come down. So what happens is the output is sensed back, and it compensates for that and drives this harder, if you like, which drives that harder and then drives these harder, in order then to regulate the voltage correctly. Because the current is obviously been pulling the supply rail down. If we didn't have that control, then the output would drop. So ultimately, with that Zenner out the circuit, we're not getting any reference, we're not getting any control, and we're not getting that locked loop, which ultimately is what we're aiming for, because the locked loop is, in essence, the output coming down in, and then in essence this is the locked loop coming back through there and then back again. So this is the, if you like, when we look at radio circuitry, we have the phase locked loop in the synthesizers. Well, this is very similar with the power supplies, in the fact that we've got this regulation loop here. Now, it is using discrete components in order to create that sensing control, whereas most power supplies, as I've said earlier, tend to use op-amps, operational amplifiers, comparators, and then it uses a reference in order to develop a reference voltage for the comparator, and then the comparator compares the output against the reference voltage. Whereas I think in this case we're using the VREF as actual regulated output to regulate the output voltage in the first place, and then it's sensed on the way back, which then adjusts the voltage drive to these transistors. Slightly different way of doing it, still just as effective, but it's just using discrete components instead of integrated circuits to do it. So yeah, that's it really. So we'll bung it back together and turn it on, see what happens. Okay then, so before we get overexcited and go and rush and plug it in, I always do a little due diligence check between the collector and emitter, the transistors on the back. The 2N3055s and 2N3771s are quite common for going short collector emitter, as we've seen on previous repair videos on power supplies like this. Now, I don't rightfully know if the transistors on the back of the unit are 2N3055s or 2N3771s. There might be something completely different, but we'll check that. But I just want to go between the positive terminal of this capacitor here, which is where all these red wires are, and the link down here on the rectifier board all together. So you've got one positive terminal, if you like, which then goes off via the red wires then to the heatsink, the 4 transistors on the back, as well as the 2 that are mounted on here. And they're all delivered directly by red wires to the collectors of the transistors, which is the bolt, which screws through to the cans of the transistors on the other side, which is the red wire. Now, all the blue wires that you can see, they're all separate emitter wires. So there's 2 blue wires which you can't see that's under this heatsink, and 2 blue wires here that go to the 2 on this side, and they ultimately come through to the front where they meet on this binding post down there. And you can probably just see, if I shine the light a bit better, you can see there's a load of blue wires there, the terminals. So that makes it easy, if there is a fault condition, for us to isolate each individual of the 4 transistors. So we're just going to go onto that terminal and onto the positive of this capacitor. So in essence, it should look something like this, where we're basically going from here with our probe, connecting from there and obviously here. And at that point, if we get a short circuit, it means that one of these transistors or more have perhaps got a collector emitter short. Now, as we've seen on previous repair videos for these high current power supplies that were repaired, some of them go collector base and emitter short, others just go base emitter short. It depends, you know, on the particular fault condition on each transistor. But we shouldn't be getting a reading while the unit's off between those two terminals. So we're going to look at that now to find out, you know, what's going on. Now we have got a bit of a strange one, because this regulator board here has got a connection off here as well. So I might have to isolate that just in case that's interfering with our measurement. But I just want to go between these two terminals. So we can sort of quickly do that then quite easily by going on to the positive of this capacitor here. So we'll just get this meter. So just double check that we're on 200 ohm scale. So just go on to the positive of that reservoir capacitor then, and then down there onto the terminals. And that's not good, you see. We're getting a very low resistor, 2.7 ohms, and that's synonymous really of the potential for a collector emitter short, and inclusive of the cabling, and obviously emitter follow resistors. I'm not sure if it's got emitter follow resistors on the hidden down there, but there'll be cement, white concrete cement resistors that have got the typically, you know, sort of 0.2 ohm resistors. So when you add all that up, that reading we were getting there appears to be correct, in line with the short circuit of the collector emitter junctions. So we can isolate each transistor individually by removing the terminal here, and then looking at that a bit further to see what's going on with each individual blue wire which comes from each individual emitter. And we can pin down which transistor could potentially be short circuit. But that measurement that we've just got there is not good. We should not be getting that. It should be open circuit between here and that terminal, that positive terminal down there, because you know, obviously the transistors are showing a short circuit condition. So let's remove that binding post terminal on the inside, separate all the blue wires from the emitters of each of the 4 transistors, and then let's take it a step further. Okay, so the plot thickens. We've got what appears to be these two terminals now, which have been separated from the positive terminal at the front. Now you'll notice there's 2 blue wires per crimp terminal, so there's a cluster of 2 transistors per terminal, if you like. So we're just going to try and pin down the problem a bit further. So just double check the meter still reads properly, and we're just going to go back on the positive terminal of this capacitor down here, and then onto that ring terminal there. So that's good. So 2 of the 4 transistors are okay, or at least reading open circuit anyway. Let's go on to this one then. Aha, so now then, so that proves that the other cluster of 2, at least one has gone short circuit. It could be both transistors, or it would be unlikely, but we have had that before. If you remember on one of the, I think it was a rapid 30 amp power supply repair video we did, we noticed that there was a couple of transistors out of the 4 which had packed in. So we could have that here again, or it could just be the one. So presumably that's going to be one of those transistors on the left, I think it is, because I think these 2 go there, but we'll just verify that. So what I'd also like to do as well, now that we've found that those 2 transistors, potentially 2 of them, are failed, I'd just like to check this driver transistor pack. Again, we've got 2 wires here which appear to go off. We've got a yellow wire. So if we just turn it round for better visibility, we've got what appears to be 2 wires that are joined together there, which is the blue and the green with the look of it. Or am I wrong? No, I'm wrong. So they've got a blue and a green. So it looks like as if, according to this, the diodes on this board here, these diodes supply power to this green wire, which then goes off, and the green wire, if I'm not mistaken, I think goes down to the collectors on those transistors, which is a stud. So let me just verify that. Yes, it does. So the green wire provides the collector current for the driver transistors at the back. The blue wire is the base, obviously that's to drive a transistor. And then what would be the yellow wires then, these are the wires which go to here on this terminal strip, then to supply the base current to all the 4 transistors on the back, which is all these cluster of yellow wires that you can see there. So that little wad of wires down there goes off then to the 4 transistors on the rear heatsink. So what I need to do, I need to effectively go onto this point here with the multimeter, and also onto the yellow wires there to check again the collector emitter junctions of these 2 driver transistors on the rear. So let's just do that now then. Let's see what we get and see whether we can put it there. Right, there we go. So I'll just double check and then just go on to what would be these yellow wires. So I'll do that on the PCB on the rear. So we need to go from there effectively. Just make sure we get on it, and then ultimately onto what is there. So that's good. We're on the yellow wires now there, and we're not getting any reading, which is brilliant. So that's good, that's good news. And I'll just double check to make sure we've got that continuity, because sometimes you can get fooled with lacquers and things like that on the PCB that are applied after the soldering, and then you think you're on the solder terminal on the PCB and you are on it mechanically, but electrically you're not, because it's insulated. And I've had that before, but at least here we haven't got that problem. So yeah, so that the collector emitter junction on the driver transistors on the back are good, which is nice. So let's just try and trace those blue wires to the appropriate terminals on the back. So I'm going to have to sort of disassemble that now. Yeah, you can tell somebody's been here before. That screw there is definitely rounded off. Nice. So we can't get that off for the moment. We can certainly get these off though, can't we? So I think somebody has definitely been and had this heatsink off before, and whoever it is, been a bit keen with the screwdriver and rounded off the screws. So we'll get this off. Okay, so we're just starting to disconnect the collectors now on the transistors, and obviously wheedle them out and just see which transistor is actually short. Now I've found on this heatsink as well, I found something new out about the power supply. We thought on the rear there was just 4 series pass transistors. There isn't, there's actually 5, because the 5th one's just here at the bottom. So the transistor at the top is a driver transistor for the whole 5 of the series pass transistors. And so basically we've got the green wire, which is the collector supply to this top transistor. The blue wire is the base supply to the transistor, the base control. And the yellow wire is the emitter, the output. And that goes off then to all the other bases then that are on the other 5 transistors. So this yellow wire comes up, solders to here, and obviously we've got a cluster then of wires that then go off to the other transistors, and they in turn are supplied by this transistor here. And yeah, so, and they are, with the look of it on there, I think the 2N3771s or the 2N3055s. Now the 2N3055s. So if we just have a look ourselves at that, you might be able to see it on camera if the text is quite clear. So there we are, look, 2N3055. And I'm not sure if it's appearing clear on there, but it should be. Might be able to get it to zoom in a bit better there. Look, 2N3055, look. So this transistor at the top's a driver. That one's still one of the series pass transistors on the bottom there. So I'm just about to put a screwdriver in there and get that red wire off. Now the problem is that the little socket thing I've been using in order to get the screw off, the thread on the stud on the bolt's too large. so I can't get the little socket on. So I'm gonna have to put some pair of long nose pliers on it, I think, or something like that, and just try and get it going, I think, or just do something, try and work out what we can do, because I'm struggling at the moment, I must admit. I managed to get this screw turn in here, so maybe put my finger on the nut. That's it, that's the ticket, that's working. So slowly but surely the nut is coming off, and then I can isolate this transistor then, because we've still got the short circuit, you see, with the other two transistors being isolated now. So let's just see if I can get that off without losing anything. There's a little washer there which I've found as well, so we'll just put that safely away, and then just remove that thing there, if you can get it off, and Bob's your uncle. Let's have a look. I don't want to lose any of the screws either, so let's just see if I can pry it off. The cables are so short on this, they must have been really tight on the cabling production line. Right, so we've got that isolated now, so that's 3 transistors in total isolated. So if we just go back up to the top, we've isolated these 2 transistors there. It's easy to remove a collector, you see, that's why we've got those red wires there. So that's the red wires that goes to those transistors on the back, and this is a red wire which goes to this transistor here. So it's by process of elimination. So let's go back onto our 3-wire terminal here. This is our 3-wire terminal, and we are going then to use the multimeter again, and in ohms we'll just touch the probes together to make sure that the meter reads okay. So we'll go on to there, and then we'll also go on to the positive of the electrolytic capacitors. And have we still got the short? We have. So the other two, one of the other 2 transistors must be short then. So we've isolated these 2 transistors, the transistor on the bottom of here, so it can only be one of these 2 transistors then. And now in my look it'll be the last transistor, so it's, you know, it's a toss-up between these 2 transistors, whether it's the top one or the bottom one. One of them's definitely gone short circuit, so let's just see if we can remove that now, which will be fun. And hopefully I might be able to remove it actually using the little socket now, because the let's see if I can get on it. I think that's the right one for it. Let's have a look. Not sure, no, that's not the right one. Oh, I think it's this one here. Right, I've got it. So let's just see if I can get on that. I'll try the top one. Whether we're lucky or what, I don't know. I might have to put a screwdriver actually in the... Oh, thought that the screw might spin, but it isn't, thank goodness. So, right, just remove that. Then we've got the little washer, and then that. So we'll just remove that now. Right, so we're only left now with 1 transistor connected after all that. So let us see if it's that transistor we've just removed, disconnected, or it could be the very last transistor. That's Murphy's Law if it is. So let's have a look. Connect our 3 terminals again and go there, and would you believe it, it's the last damn transistor, isn't it? Or the 5th transistor, the very last one. Ah, dear me, can you believe it? Right, so let's just remove that then, that binding post, and then we'll come back. Okay, so we've isolated this transistor here at the bottom, this one that we suspected, that definitely had the collector emitter short. So we've isolated the base connection, which is the yellow wire here, and this is the wire that leads off to that transistor. We've unsoldered it. So now we've still got the cluster of base connections to all the other transistors, and we're just going to make sure now if that fault's cleared or not. So we're going to go on to the 3 wire terminal. Don't forget these, this that has 2 wires on it and that connect together. and the stud terminal at the front, so we'll check them both. So if I make the emitters positive, because they're NPN transistors, you shouldn't be conducting. When I make the base negative, and that's cleared that fault, so that confirms there was 2 countable faults with that transistor down there. One that it gone collector emitter dead short, and also the diode path between the base and emitter junctions reading both ways, and it shouldn't be. Now we've isolated that transistor. It means all the other transistors, the 3 of the transistors out of the 5, are actually okay. Now we've got the other terminal that I told you about, which is this one. This connects to just 2 of the transistors on the back, and so we need to just double check that as well. But before we do that, let's just return back now to making the emitter negative on those 3 transistors and the base positive. We should be getting a reading, and we are. And as we verified, when we make the emitter positive and the base negative, we're not getting that reading, which is what we want. So that proves 2 countable faults for that 1 transistor alone. So now we'll do the same. We'll make the emitters on the other 2 transistors positive, and then we'll go on to the base. Now we shouldn't be getting a reading, and we are now then. So this again shows that there's another transistor that's faulting a different way. The other 2 transistors, one of which, or both, might have a problem with between the base emitter junction only, because the other transistors are not showing collector emitter short. So one of the other 2 transistors on the back has got a base emitter junction problem. So it's reading 933 that way, and if I turn it round so we make the base positive and the emitter negative now, what reading do we get? We're getting a lower reading. So we've got a leaky junction between the base and emitter on 2 transistors, and that confirms it. So which 2 transistors are they then? Let's see whether we can find that out from this labyrinth of blue wires. So let's just tug on one first. And where does that go then? That seems to go around that way, if I'm not mistaken. Yeah, it seems to go there to that. So that's one blue wire. The other blue wire then, what's that one then? Where does that go? Is that one? Yeah. So it's one of these 2 then, on this heatsink here, has got a base emitter leak. So we've probably got 2 transistors out of the 5 that are stuffed. So we will just have to go and check that, I think. Don't know about that. We'll have to check this top one here, this driver one, separately from this board. But yeah, so that looks okay. That transistor base emitter collector emitter. That one's faulty. That one's good. One of these 2 then has got an issue. So instead of trying to, I could remove the base again. That might be easier actually. I'll just find the wire then from one of those, because they're all twisted down there, and then we'll remove that wire one at a time, and we'll see which one of those 2 transistors is faulty on this side. Okay, so remove this transistor now from hopefully. It might be Hitachi that makes for RS. So I'll bob that in and put some silicone heatsink compound on it and go from there. Okay, so we're all back together now. Everything's all back as it should be. All the wires for the collectors and base emitters, etc., all back in, soldered on the board. Everything's wonderful. I just want to do a check now before we switch it on to test it, to make sure that the screws for the collectors on the transistors are actually in the correct place, because if not, then what can happen is that the DC supply gets shorted, the supply to the collectors. So all I'm doing basically is I'm just going onto the transformer earth lug there, and then on ohms, 200 ohm scale, just going on the collector, just to make sure that there's no short. And because the collector's all joined together, we shouldn't have a short anyway down to chassis, because ultimately that causes a massive short circuit and a major fizz bang. So yeah, everything's okay. What we're going to do is we'll just put the lid on, just to make sure that if anything does go fizz bang, we don't end up with a capacitor embedded in his forehead or anything like that. So we'll just make sure we've got the lid on before we hit the switch. Okay, moment of truth has arrived. Let's hit the switch. So far so good. No fizz bangs, smoke, flames, anything like that. We're on DC volts now, and we'll just check 13.87 volts. Wonderful. So I think next thing to do now is just put it on load and see what voltage it manages to maintain then. But all is good so far. So excellent. It looks like we've done a great repair job on that. So let's load it up and see what it does. Get some big resistors on the go, which I've got here. So here we go. Okay, so now we're ready to do another test, which is a load test. So what we've done, we've set up a couple of basic instruments here. I've got the old-fashioned ammeter here that's on the 50 amp scale, and we're using the 50 amp tap on the top of the meter there. We've got two big power resistors here, which do get very, very hot and can burn out if we're not careful. So we have to make sure that we only load the power supply for just, 10 seconds at the most. Otherwise, these are just going to start frying. We've got the voltmeter, just a basic voltmeter. You don't need fancy test equipment. Just, basic voltmeter. We're reading the output currently at 13.87 volts regulated. Now, the value of resistors that we've chosen here are going to roughly put the power supply on potentially a 50% duty cycle, a 50% load of the output rated current. So what we're going to be doing is we're going to be testing it at around about 15 to 16 amps, so about half its rated output really in current consumption. So we're going to do that now. We're going to put it under load. So I'm just going to verify that the power supply can maintain a significant load, as well as maintaining a voltage here within a close proximity to 13.8 volts. That's the ultimate test really, that the series pass transistors are performing correctly and that the power supply is living up to the stresses that we're going to put it under. So here we go. We're just going to, obviously half a scale is 25 amps, full scale is 50 amps. So we're just going to put it under load now, and there we are, look. So we've got about 15-16 amps being drawn there, and we've got a voltage of 13.75 volts DC. So that's lovely. That proves that the power supply can be put under load, and that's getting very, very hot now, is that resistor. It's just about to burn my finger, so I'll disconnect that before it starts frying. So yeah, that means that why, that is hot. Whew, you could fry an egg on that now. But yeah, that sort of proves now that the power supply itself is repaired, and that's wonderful as far as I'm concerned. That's a good result. Now obviously this power supply, unfortunately, like so many power supplies, tends to come with short circuit protection. So obviously when we load this to a certain point, obviously short it out, the output current is measured by the PCB internally, and then it removes a drive to the series pass transistors on the rear. And obviously in our situation we had a couple of faults on this, but while we were looking through that, I could see no sign of any crowbar circuit on the output. So obviously, as in our case here, we had the ST2N3055 transistor that went collector emitter short. Obviously, the collector of a transistor, which is the casing, is connected to what would be the VCC rail from the smoothing reservoir capacitors and the bridge rectifier, or the full wave rectifier in this case. So you're looking at probably 30-40 volts DC on that collector, and then ultimately then with the emitter, when the emitter legs will connect off then obviously to the output terminal. And so power supplies like this that are made to a particular price point tend not to have emitter follow resistors, which is the case with this power supply. So you know, the difference in HFE between multiple transistors is very slight, so ultimately one transistor is flogging its guts out more than the others. So rather than sharing the load equally by using emitter follow resistors, which is a common practice on many decent quality power supplies, this one doesn't have it. And also what it doesn't have, which quite a lot of power supplies that I see, it's not just these sort of cheaper brand power supplies, but it's even some of the more expensive ones that I've come across on this channel that we've done repair videos for, if you have a look. They don't have a crowbar circuit on the output, and I've got some devices here, some diodes, that once the output voltage here would essentially go above, say, 16 volts DC, it would immediately short circuit the output and pop a fuse, or that kind of thing. But this power supply doesn't have any protection on its output for over voltage. Now, it's quite common, I don't know why, but these ST series 2N3055 transistors, as you'll have seen on my earlier repair videos with power supplies, if you look on the channel, the power supplies that we've done repairs of that are being used in the ST branded transistors tend to go collector emitter short. And that means obviously the high voltage which is applied to the collector, it makes its way out then to the output terminals, and then obviously if you've got a very expensive piece of equipment on the output, be it a radio, communications, transceiver or something like that, invariably extremely expensive pieces of kit, boom, that's it, you blow it up. So this is a sort of danger point really, a lot of power supplies that I come across that repair on this channel, is that they advertise quite frequently on power supplies short circuit protection, regulated protection, you know, that maintain a regulated output, particular voltage under certain load conditions, but it doesn't mention anything about a crowbar circuit. And quite often these power supplies, you'll find them, they'll have a mains fuse but they won't have an output fuse. So it's only when you get to really expensive power supplies, the very high quality, the top end of the range, where you see those kind of features. So it's always worth, when you're selecting a power supply, looking at the overall features that the power supply has. Does it have not just short circuit protection, does it have over voltage protection? Does it have an output fuse? You know, is it fan cooled? Does it have a temperature cutout on it? So if it gets too hot, will it actually turn the power off until it cools down? All these things are all important factors to consider when you're selecting a high current power supply. Now, that doesn't mean this power supply isn't up to the job. It's just designed for a particular price point in the marketplace, which tends to be at the low middle end of the market range. Now, perfectly adequate for anybody to use, but unfortunately, if you get these transistors go collector emitter short, there's no protection on the output, and thus, you know, you get high voltage output coming out. So yeah, but I must say though, that tends to be quite common with the ST transistors, the collector emitter short, and I haven't seen that problem so much with other brands of transistors. So there must be something about these where that is commonplace. The other thing as well that I noticed on this is that there were just mica washers on the back of the transistors, and they were fastened in without any heatsink compound as well. So potentially these transistors can overheat, you know, and obviously the temperatures that they might get to under constant load may cause faults within them, baking them, things like that, potentially. Depends on how the power supply is used. Obviously these power supplies, although they advertise this high current, they can't maintain that for any length of time really, just a few minutes at a time maybe, because they'll overheat. There's no fan cooling on it, there's nothing really. All the components inside will be running to maximum threshold at 27 amps, and they'll soon overheat, and the transformer itself will start to overheat. So Again, a lot of power supplies in this sort of range don't tend to quote the duty cycle rating, so you could potentially overload the supply without realising it, particularly if you're using it, say, with a radio transceiver that draws about 20 amps and you're constantly transmitting in conversation with someone for several minutes or maybe a couple of minutes, and it can put the power supply under immense load and ultimately overheat the power supply. Especially, you know, if the duty cycle, the transmit-receive cycles are quite short and frequent. So, yeah, these are all considerations about these sort of power supplies when you're looking into it. Of course, you could add a fan yourself on the back, or you could put forced air cooling, something like that, which is a good idea to keep them cool. But, yeah, it's just basic things, really, looking at it. But yeah, I've really enjoyed the video. It's been really good. We've obviously found multiple faults on this power supply, not just one fault. We've used the mathematics to work back in the formulas of how to calculate when we're using the Zenner diode and resistor, potential divider, voltage dropper circuit. We've then used that mathematics to then backwork the equation so that we get back to the source voltage, so we can prove that the formula that we've used was correct and working properly. We've obviously calculated volts, current and resistance without knowing either one of those three, by using other things such as, you know, calculating resistance from voltage and current. Obviously backworking the formulas in many different ways, as you've seen, and the working out methods in order to be able to describe the circuit function and the wattage of resistor, and also analyse the power supply in a greater context, where we've looked at the design of the power supply using a full wave rectifier, smoothing capacitors. Again, in these, only time that the smoothing capacitors, not very well rated for peak inverse current, which you tend to have with the bigger sort of beer can sized capacitors, what we used to be called in the good old days of computer grade capacitors. So again, all sorts of different quality issues around the build of this power supply as well. So lack of heatsink compound, the lack of output protection, no emitter follow resistors, lots of things really that, you know, stand out as part of this sort of design. But yeah, wonderful. Really enjoyed it. Hope you have. Stay tuned for further videos that will be on the channel regarding power supply repairs and other things. Always an interesting thing to delve into. But at least you've seen, you know, you get multiple faults sometimes. So it's always good to be cautious and never rush into things, and just try and methodically work through and problem solve in order to get the desired outcome, which is obviously repaired power supply. So with that, thank you very much for watching. Take care and catch you again in the next video. Bye for now.